People write a chat.
Sorry. So for the introduction, this microphone will be picked up on Zoom. You're welcome to either hold it or wear it or you can click up there. And then you may use this microphone to project to the room.
Okay, great.
It should be okay. That's test 1, 2. Seems okay. Perfect.
Okay, hello everyone. Let's get started. Just a quick note before we do the introduction. I've been told to remind everyone to please pick up plates and cups before leaving the room. So do make sure to do that. Okay, so welcome everyone. Today is the third day of the 2024 Nobel Lecture Series, and we'll be hearing once again from our speaker this year, Professor Ellie Zipperman. Today's lecture will be titled Getting Ocean Technical: Is the Resonant Wave Interaction Approximation Consistent with the Dynamics of Internal Wave Fields? And also, what sets the mid-depth ocean stratification? I think we're all in for a treat, as ocean dynamics has been one of the pillars of Professor Zipperman's scientific research since the beginning of his career, starting with the completion of his PhD in physical oceanography at the Woods Hole Oceanographic Institute and MIT. And this work, of course, was followed during his time as a scientist and eventually professor at the Department of Environmental Sciences in the Weizmann Institute of Science. So please join me in welcoming our speaker and the third day of our lecture series.
Thank you. Great, thank you. So maybe just a bit lower volume, if that's okay. Can you hear me okay at the back today? I think this might be just a bit too high. Okay, so two subjects, and I'd like to start with the second one. Great, perfect, I think. How's that? Thank you. Okay, so I'd like to start with this one, actually. It's a bit less technical. So the question is, what sets the exponential mid-depth stratification of the ocean? Here's what it looks like. And we have the laser pointer. So you look at the stratification from 1 kilometer depth in the ocean to 3 kilometers, and it's perfectly exponential, right? So the question is why it's so perfectly exponential, and there are going to be two explanations, and I'm going to show you that they're wrong and we are right. How about that? That's the plan. Okay, you get the spirit. So why do we care? And this is also related to the question of, is AMOC adiabatic or diffusive? So just to remind you, AMOC, the Atlantic Meridional Overturning Circulation, you have this water flowing north, sinking and returning. The question, so this is a super unrealistic schematic, but it's helpful to look at. So the question is, when the deep water goes back, is it upwelling only in the Southern Ocean, or is it upwelling everywhere due to diffusion? So that would be part of the question, and I'll talk about this a bit more later. So this is what this looks like. If the circulation is adiabatic, what does it mean? You have this water flow going northward, sinking in the North Atlantic, returning along isopicanal, so no mixing throughout, and then coming up to the surface in the Southern Ocean, all of that with no mixing along the way. That's one scenario. The other scenario is that it's coming back through diffusion here. So the circulation is able to leave an isopicanal surface because there's mixing and go up as upwelling in the interior. So these are the two options. Either the circulation goes along an isopicanal with no mixing whatsoever all the way from the North Pole to the South Pole and upwelling in the Southern Ocean, or is it upwelling everywhere? And this is coupled to what sets the mid-depth exponential stratification, as you'll see. So these are the two questions we're dealing with. Why is it exponential, and is the AMOC adiabatic or not? So again, so this is the question, why is it exponential? And there are going to be two contenders for the theory. So the first one is due to Monk, 1966. He noticed the following thing in that paper, Abyssal Recipes, which is a classic paper, that this exponential shape that he found can be fitted by the solution to this very simple balance for the temperature. So vertical advection balanced by vertical diffusion. If you choose appropriate values for the vertical velocity and the diffusivity, 10 to the minus 4, then the solution is exponential and it looks like the observation. So that's the first contender for explaining the exponential shape of the mid-depth circulation. Any questions about this explanation? Okay, yes.
Why would the vertical velocity be constant?
So he just said if it's constant and if the diffusivity is constant, then that's what you get. You know, we'll talk about what happens if it's not constant. There's no reason for it to be constant, neither W nor kappa. Okay, great. Okay, so if you look at this, so no, that was a paper from 666. You look at this and you see in the North Atlantic, South Atlantic, North Pacific, South Pacific, the stratification, the density is always exponential. You even look at the vertical gradient of the stratification, it still is pretty close to exponential. Not as good. You take a derivative, introduces noise, obviously, but the stratification is very robustly exponential. So there is something to explain here. It's not just one profile in the Pacific for Monk's observations. Okay, what's the problem with that explanation that we just talked about, contender number one? When people do these tracer release experiments, so you go into the ocean somewhere, this is the longitude and latitude, and you release tracers, and you come back later, a few months later, and you look for the tracers, both horizontally and vertically, and you see how rapidly did these tracers spread horizontally and vertically. You can deduce the mixing from that, and the mixing turns out much smaller than what Monk required for this exponential profile. So that's the problem. That explanation was wonderful, but the mixing that he relied on was much too strong relative to these tracer release observations. Okay. Great. So what's the second contender? It's a bit more complicated. So what are we looking at? This is the isopycnals, so surfaces of constant density in the Southern Ocean. So this is Antarctica here, going toward the equator here, and looking at the depth from the surface to -2 kilometers, and you see the isopycnal slopes. So let's discuss what sets these isopycnal slopes. It turns out to be a competition. On the one hand, you have Ekman-driven, so wind-driven Ekman flux. So the wind is zonal, and this leads to a northward Ekman flux in the southern hemisphere. And this tries to straighten these, steepen these isopycnals, right? The wind-driven circulation goes in that way, and it tries to steepen these isopycnals. And then there's a competition between that and the eddies, the ocean eddies in the Southern Ocean that are very dominant, that try to flatten the isopycnals. So there's a competition between eddies and Ekman transport. So the eddies versus wind. And this competition sets the slope of the isopycnals. And if you think about it, this slope of the isopycnals in the Southern Ocean translates this surface density to this density right here. So this is how the mid-depth stratification is determined in this theory. The slopes are determined by this competition between the wind and the eddies. And these slopes translate the surface density into the mid-depth stratification. So that's contender 2 for what sets the mid-depth stratification. This goes well together with the idea that the AMOC is adiabatic because these slopes are part of the upwelling path of AMOC. Questions about contender number 2? Should I repeat any of this, or was that? Yes.
So thinking back about the 10 to the -4 value.
Okay.
Yeah, so the lead well was that was very much better than particular like South Atlantic.
That's right. Yeah.
But I mean, there are other turbulence measurements that actually support that larger value, or are those more like in the mixed layer? I don't know them well.
I'm going to show these in a second. So close to boundaries, close to topography, the mixing is large. That's going to be an important part of the story. So, but I think it's agreed that low value, 10 to the -5 instead of 10 to the -4, represents the ocean interior away from boundaries. But I'll talk about these in 1 second. Okay, great. So this other theory now tells us that the slopes in the Southern Ocean are determined by a competition of wind and eddies. This is what's known as the Gent-McWilliams coefficient. It represents the eddies. The tau is the wind stress. So this competition sets the slope, and the slope sets the stratification right here. This is the northern part of the Southern Ocean, and here's the mid-depth ocean, whose stratification based on this is determined by the eddies and the wind. Does that make sense? I don't want to lose you that early, so please ask a question. Okay. Great. Let's see. So, great. We talked about AMOC being adiabatic in that picture. So here's what happens if you now take an ocean model. And these are two different papers that basically looked into this. You take an ocean model, you set the diffusivity to be very weak. So you get this adiabatic AMOC, and now the mid-depth stratification is set by the Southern Ocean wind and eddies. So even if you didn't follow the exact details, here the stratification between 1 and 3 kilometers in the ocean is set by the wind and eddies in the Southern Ocean, okay? In that case, you look at the profile of stratification. This is DDZ of the stratification. You see it's very far from exponential. So the idea that AMOC is adiabatic and there's no diffusion and the Munk picture is wrong also doesn't lead to something that we can live with, because the stratification is so robustly exponential, and this picture does not lead to an exponential profile. So this is our second contender failed in the very basic test of producing an exponential stratification between 1 and 3 kilometers in the ocean. Okay. So let me summarize the problem. So we had two ideas. One is that the mid-depth stratification is determined by this Munk balance of vertical advection balanced by vertical diffusion, but the observations show that KV is much too small for this to be consistent. So that wouldn't work. Two, there was the idea that the Southern Ocean winds and eddies set the stratification through this balance, but this doesn't lead to an exponential profile. It leads to a stratification, but not exponential stratification. So that's the problem we're faced with, and that's what we're trying to solve. Any questions about the question? Okay, the two contenders are clear pretty much. Great. Okay. See people nodding. I guess that's a good sign. So what are we going to say? We're going to suggest that the mixing does happen, except it happens not in the ocean interior where these tracer release experiments happen, but close to the boundaries. Boundaries means mid-ocean ridges and ocean boundaries. There's strong mixing there. I'll show you evidence. And that can lead to an exponential stratification everywhere. That would be the idea. So here's some observations. So this is then the Brazil basin measurements, and these are other measurements that show how the diffusivity is larger as you go close to a mid-ocean ridge. So basically, the diffusivity in the ocean, the turbulence can be larger as long as you're staying away from the middle of the ocean and you're only close to the boundaries. So the question is, can we use that mixing to explain the exponential stratification and still be consistent with the idea that the mixing is small away from the boundaries? So to look into that, we ran these experiments. So this is Madeline Miller and Xiaoting Yang, different papers. So this is a run in which we call it min-max, so minimal mixing. This is the Southern Ocean, this is latitude, and this is longitude. And there's just a small diffusivity everywhere. We know that this doesn't lead to an exponential profile. That's what these other papers did. This one is one in which we have a large, this should have been 10 to the minus 4 here. So in this case, we have large mixing. We know that this leads to an exponential profile, but this value is not consistent with the observation. And in this case, we have weak diffusion everywhere, but on the boundaries in the west and the east, we have higher diffusivity. And this higher diffusivity then will hopefully lead to an exponential profile here. So again, this is marginal mixing. So we are hoping that large mixing along the boundaries in these two areas, this is the Southern Ocean again, the channel, the Southern Ocean channel. We're hoping that mixing along the boundaries, consistent with observations, with very weak mixing in the ocean interior would lead to the observed exponential profile. So let's see if that's, any questions about these experiments? Is it clear? Great. Do you love this Mach thing? Look at that. So much better, don't you think? Great. Okay. So these are the results of the 3 experiments now. So in this one, the minimum mixing, one doesn't get an exponential profile that fits the right length scale. You know, it needs to be an exponential profile with a length scale of about 1 kilometer, and one doesn't get this here, and we knew that, right? in this Monk mix experiment, one gets an exponential profile, but the mixing is large everywhere, so that's not physical. But in this case, where we have mixing only along the margins, one does get an appropriate exponential profile, and the mixing in the interior is small, so that seems to resolve the problem, actually. So we think that could be a solution for what sets the mid-depth ocean stratification. You simply have large mixing along the boundaries and weak mixing in the interior. It's consistent with the observations, and it gives you an exponential profile and everything okay. So what happens is along these boundaries, one has a Monk balance with very large diffusion and very large upwelling, and then ocean eddies transport this exponential stratification toward the interior along isopignals, and then you get the exponential stratification everywhere, not just along the boundary. So that's how this works. The Monk balance WTZ equal kappa TZZ along the boundaries, and then eddies carry that resulting exponential stratification into the ocean interior and setting an exponential stratification everywhere. Great. Yes. Was there a difference? It looks like there is a small difference. I'm not sure what to say about that, admittedly. Yeah, there's some difference here. Did you have something specific in mind? Yeah, I mean, I think all of them have some mid-depth stratification. Remember, we're interested in the part from 1 to 3 kilometers. All of them have some stratification here. I think all these 3 pictures are showing is that generally all of them produce a picture that seems reasonable. But when you look at the details, this one doesn't have an appropriate exponential profile. This doesn't have an appropriate exponential diffusivity, and this one seems to be a good balance of the two. You know, it's such an idealized ocean that, you know, if you think about it, just a Pacific Ocean, square domain, no North Atlantic water, you know, it's basically just one basin. It's difficult to worry about the precise temperature of the bottom and so on. It's just too idealized. So we're trying to make a general point here. Great. Okay. Never mind this. Okay, this is the point that was mentioned before. So now it turns out you can take that Monk balance, so WTZ equal kappa TZZ, and you can solve for it. You can solve even when W is not constant. If W or kappa are a function of Z, you can still solve for the temperature from that balance by using 2 integrals. And turns out because you integrate twice to get the temperature, to get this analytic solution basically, the 2 integrations give you an exponential profile even if W is not constant. So I suppose you look at this, and this is the marginal mixing experiment that we're relying on, and you can see that W is not constant; it's varying a lot. And this is another one. And in spite of the fact that W is changing a lot, the stratification is exponential because of these 2 integrations, essentially. And this demonstrates it here. So we start with a W that looks like this sine wave, and you still get a temperature that is very much exponential. This is the TDZ. It's less exponential, but you get the picture. Because you have 2 integrations going from W to T, the T can be exponential in spite of the fact that W is very much not a constant. So the explanation is very robust. It doesn't rely on W or kappa being constant. Yeah.
Is this like a sampling of things you've done, or is there a reason that W itself? Is this an output of model?
Yes, this is an output of these experiments, and it's basically making the case that we showed the profile to be exponential, but that doesn't mean that W is constant. And then we're trying to explain why is it still exponential in spite of the fact that W is not a constant. The explanation is that there are these 2 integrations, and a further demonstration of that is this, where you take W to be some sine wave and you still get an exponential profile. Yeah, in this case, the other one, W was the output of the model. In this case, W just a prescribed, just to show, yeah, exactly, yeah. Yes?
So because there's that integral of W with respect to Z, it looks like it's kind of mean. vertical velocity doesn't matter, the sign of that is like positive?
Yeah, no, I mean, you want the general values to be reasonable for this to work. So in the boundaries, W is large and kappa is large, and that somehow balances. Now, what's important is not W or kappa, it's the ratio of W and kappa. So in the boundaries, you have large kappa and large W, and that leads to the right exponential scale in the interior, which is then advanced by eddies into the ocean interior. Okay. So another test that we could make, yeah, we're doing well on time, is in this idea that the ocean eddies and the wind sets the slope and that sets the stratification in the interior, the interior stratification should not depend on kappa. So this is an experiment in which we're actually using an eddy resolving model. That's a different paper. We're using an eddy resolving model, so there are plenty of eddies in the Southern Ocean, and we change the diffusivity from 10 to the minus 5 all the way to 10 to the minus 3. And you would think that and this diffusivity is changing only in the interior, not in the Southern Ocean. So if what sets the stratification here is the wind and eddies in the Southern Ocean, then these slopes in the Southern Ocean should not depend on the diffusivity in the interior. But what happens is you change the diffusivity in the interior, and this changes the slope in the Southern Ocean. So that to me says the slopes in the Southern Ocean are not determined by the wind and the eddies, yes. Instead, they're actually slaved to the interior, whose stratification is set by this mixing, maybe by the marginal mixing. That's the idea. That another proof that it's not necessarily the wind and eddies in the Southern Ocean that sets the slope, that set the interior stratification, because if that were the case, these slopes would not depend on the mixing here. So is the point clear? I did promise that this will be more technical this time. I apologize for this. Any?
Balance, so all of these are balances, so that's not a categorical statement, or just that.
I would say not. It's not either that or this. I would say it's not. I think it's safe to say it's not just the wind and eddies in the Southern Ocean. How about that? I think that I would feel comfortable making that statement. Great. Okay. Great. So to conclude, so I showed that the observed interior mid-depth ocean stratification is very robustly exponential. We've known that since Munk 1966. Observations showed that the interior mixing is weak. These are these tracer release experiments that were wonderful advance at the time. But the mixing is also known today to be strong near boundaries, including mid-ocean ridges and so on. So these recent ideas where the AMOC is completely adiabatic and the Southern Ocean wind and eddies determine the mid-depth circulation, mid-depth stratification lead to a non-exponential one. Something happened there, I think. Can you still hear me okay? Okay. So, these ideas that AMOC is adiabatic and the Southern Ocean eddies and winds set the stratification don't lead to an exponential stratification. So we think that strong dipycnal mixing close to the ocean boundaries communicated to the interior using ocean eddies can lead to the right answer. And this picture reconciles, on the one hand, the idea that interior ocean mixing is weak, on the other hand, the idea that the stratification should be exponential. So I think that's a good balance. And admittedly, this is an example of the idea that scientific progress is made one funeral at a time, because this is a result of my PhD, 1986, and I just couldn't let go when ideas that are different from what I said in that thesis came up. I just had to show that they're wrong. So we'll have to wait for my funeral for this progress to be made. Any questions? Yes.
So, what generates I speak to the stratification, and what's the time scale for the
For the eddies, you mean? Okay. So you have these very small regions close to the boundaries where there's turbulence because of the location of the boundaries, maybe breaking of internal waves and so on and so forth. This leads to strong mixing. This also leads to strong upwelling. And W over kappa would be such that you get an exponential length scale of 1 kilometer, which is what Munk predicted. Now you have ocean eddies that work along isopycnals. They carry the information from the boundaries to the interior along isopycnals and set the stratification to be equal to what was determined on the boundaries everywhere. And that's how this works. We're talking decades at the most, I would say. What do you think, Nico? Decades. So vertical mixing is hundreds of years, and ocean eddies are decades. I think that would be roughly fair. Okay, more questions about this part? It's going to get much worse after this 1/2, so please brace yourselves. The Southern Ocean timescales are shorter again. Yes, that's true. Yeah. The eddies and the wind, the Southern Ocean is again a shorter timescale. I would agree. Yeah. Yeah, I think the good place to look at that is without one of those initial figures. Yes, so you see this is a nice schematic by Paolo Cesi. So we're talking about this mid-depth circulation, but in addition to that, there's the sinking from the Southern Ocean that goes deeper. So that sinking is under the stratification we're talking about. Okay. Trying to, every time the camera points into my face, I turn around. How's that working for you? Okay, great. So I want to go to the other half, which admittedly is a bit more technical. This is with my wonderful collaborator, Golan Bell. We've been struggling with this forever. We submitted one paper. So far, we got reviews. We're hoping to be able to answer the comments soon, but it's something we've both been passionate about, and it takes us forever. And we don't even have a single paper about this, but we still love this work. Anyway, so let me start slowly. So what are ocean internal waves? So this is depth. You see this goes from the surface to 30 meters. This is time. And you see the temperature going in waves, this as function of time in a given location. And these waves are internal waves, right? I guess everyone knows what internal waves are. And you all know that the group velocity and phase velocity are perpendicular to one another. And this is the signature of internal waves at the surface. So when there are internal waves, you do have some surface signature. And I know that some people here work on that sort of thing. Internal waves are a big part of the ocean circulation. They're important because one, the mixing due to the breaking of internal waves is the mixing that we talked about in the previous half of the talk. So these internal waves are super important in leading to this overturning circulation. And also the internal wave interaction sets the spectrum of internal waves. So there's the famous Garrett-Monk spectrum that looks like this. In this case, it's the frequency, but you could also look at the wave number spectrum in the vertical and horizontal. These are classic pictures from this old Garrett-Monk paper, 79. So it turns out that there is a universal spectrum for internal waves, and a goal of this research area has been to explain that spectrum. And one of the tools is something called the kinetic equation, which I'm going to look at. So the two goals typically of this internal wave research is understanding the spectrum and predicting the mixing that is important for the large-scale circulation. Okay, so the whole idea is based on something called triad interactions. So in general, you have nonlinear interaction between three waves. This is directly from the momentum equations, no approximation made, only if, say, the one wave number is the sum of the two others. There's actually some refinement here, plus minus, but never mind. If you have a triad of wave numbers, then these three waves, K, P, and Q, can interact. So I'm going to talk, everything here is going to be in 2 dimensions, one vertical and one horizontal dimension. So when the three wave numbers can form a triangle, they can interact. And the claim of this resonant triad interaction, which is an old idea, is that the interaction between these wave numbers is especially efficient if the frequencies also form a triad if you want, if W of one wave is equal to the sum or difference of the other two waves. So that's the idea, where W is given by the dispersion relation. So this is actually another equation relating Kp and Q. So this here is a function of Kp and Q, and therefore this using this dispersion relation. So these are both equations for Kp and Q. Make sense? So the idea is that waves will only interact efficiently if both equations are satisfied. So this was studied by Phillips 1961 just for 3 waves, and the idea was developed into a theory for a field of waves by Hasselmann 1960s. He actually talked about 4 waves interacting for surface waves instead of 3 internal waves, but same ideas, very, very important papers, both this one and this and these. So is it clear what triad interactions are? So triad interactions is when you have 3 waves interacting and satisfying this. Resonant interactions is when both this is satisfied and this is satisfied. And the claim is that if both conditions are satisfied, the energy transfer between these 3 waves is especially efficient. Make sense? So that's what resonant interactions are. Questions? You wanted to ask something? Okay, great. So if you ask, okay, what K values solve these 2 equations, you can plot this for a given K value. K is 12, 24, whichever, as function of, so remember, Q is simply K minus P. Let's keep it simple here. And so Q is known, we specify K, so now we can plot as function of P, where are these 2 conditions satisfied? So if this is Px and Pz, the 2 components of the wave number, these 2 equations are satisfied along these lines in wave number space. So instead of having to worry about all P's, we just have to worry about a certain small set of wave numbers P that interact with K and Q and give us this nonlinear energy transfer. So these are the resonance curves. These are the curves in wave number space along which these 2 conditions are satisfied. Okay, so this condition can't be satisfied for any KPQ. They have to be satisfied only over a certain range of curves, and these are the curves over which it's satisfied. Great, so what do we want to do? We want to use idealized direct numerical simulations of a field of random internal waves to test the resonant interaction idea. We want to see whether this indeed is when efficient interactions happen. And we do this in a very, very idealized, non-realistic, admittedly, simulation. It's going to be two-dimensional double periodic. The resolution is not amazing. It's just surprising how much computer time and storage this actually takes, because you have to store your solution every 18 seconds, and it's terabytes of memory. So even though this looks like a simple problem, it ends up that this takes forever to compute and lots of storage space. So that limits our ability to go into higher resolution. So you see 3 simulations here. One has strong forcing, one has medium forcing, and one has weak forcing. The resonant wave interaction theory is meant to hold for weak forcing. Our medium forcing is sort of an energy range that is typical in the ocean. So the weak forcing should definitely have led to something that is consistent with these ideas. And you see the spectra here in the terms of the vertical wave number and the horizontal wave number, this horizontal and vertical. Okay, and these are the energy time series normalized by the standard deviation. And so you see we run this after reaching an statistical steady state. We run it for 200 days, and then we analyze these 200 days to see where is the interaction happening and so on. Okay, so this is the surprising result we ran into. So the energy equation looks basically like this. There's other terms, but this is the nonlinear transfer. So you have the energy at the wave number K is influenced by interaction between P, Q, and K. This is some coefficient of interaction. And this is the enforcing the triad in wave numbers. And now we can look at this term and see how big is this interaction term as function of Kp and Q. Is it large only for resonant interactions, right? So we take the results of the numerical model, transfer them to K-space, and then plot them like here. So you can see here a zoom in into a certain range in the weak forcing case. So the interaction should, this part right here, should have been large along the resonant curves, and instead you see that it's large elsewhere, and it's not necessarily large along the curves. Okay, so this is the main result, so I want to emphasize this and explain this again. Okay, so what we see, this is the interaction between the waves that lead to changes in the energy of wave number k. And the interaction involves P, Q, and K, the three wave numbers. So we know what the resonance curves looks like. Along the curves is where we expect the interaction to be especially strong. But we can actually go ahead and calculate this form. I mean, it's a bit painful and time consuming and storage intensive and so on, but we can calculate this. And this term is shown by the colorful pixels. And you see that the colorful pixels are not arranged along the resonance curves. So it seems to suggest that the strong and efficient interaction doesn't necessarily happen along the resonant curves. Does that make sense? Any questions? This is the main result which we're trying to explain. So please ask me if there's, yes, John.
Yeah, so you're showing us a triple correlation. But when you're on resonance, those don't necessarily lead to energy transfer. But you can have large terms that don't have energy transfer.
So the large term that don't have energy transfer. So we looked at two different things. We looked at the RMS of this, and we looked at the time mean of that. Both of them are not large along these resonant curves. Does that answer your question? Because I'm not sure I got it.
Not all triads. Some of them are found that don't but they're correlated. In other words, they're telling you about how the waves arrange their phases with respect to each other, but they're just stuck there and they don't transfer the energy. So is the interpretation that the energy transfer is not happening where you think, or is the energy transfer that there are other correlations that are larger than the ones you thought?
Yeah, I mean, you see many curves here because there are like 6 different resonances, depending on whether it's K plus, P plus Q, P minus Q, omega P plus, omega P minus, and this is a cubic equation in terms of the dispersion relation. So there are several actually resonant curves, and we're actually plotting all of them here. All of the lines correspond to all of the possible resonances. So what you're saying is that maybe only one of these lines, say the dash red, should have shown large interaction, but it looks like none of them actually shows large interaction. Does that answer the question? Okay, great. Okay, so the question is, why don't we get strong interactions along these resonance curves? What broke down in the approximation? Of course, our simulations are super idealized, 2D, double periodic. That could be the problem for sure. The resolution isn't perfect. That's the first thing to blame. This is the bigger picture now. So instead of a zoom into this, I think this is a zoom into this case, you can see the fuller picture of our simulations, and you can see that the areas with large interactions are not necessarily on the curves and so on and so forth. So why does this break down? So, and these are the strong forcing case and medium forcing case in which the situation is even worse. Okay, so why didn't it work is the question. Okay. So to understand that, we do need to look at the derivation of this kinetic equation. So I have just 2 slides with equations showing the derivation of the kinetic equation in order to understand why we think the derivation failed for our particular situation. Okay, so bear with me here. We start with momentum equations for the horizontal velocity and vertical velocity, and the buoyancy equation, the mass conservation. We derive a vorticity equation. I mean, this is a standard derivation that people have been using for this particular 2D problem since the 70s. We didn't invent anything here, right? So we derive a vorticity equation and use a stream function formulation, and then we end up with 2 equations. One is the vorticity equation, and one is the buoyancy equation, both written in terms of zeta, the vorticity, and psi, the stream function. Okay, now we take these 2 equations and we Fourier transform them, again, following standard procedures. We didn't invent anything. And after Fourier transforming, we define a wave amplitude equal to the vorticity divided by k plus minus 1. S is plus minus times the buoyancy, everything in spectral space. This A turns out to be the wave amplitude. So it's easy to show that this actually is the wave amplitude. And the energy equation looks like this. This is the energy. So the wave amplitude squared is the energy. And these are dissipation and so on and so forth. This is the important one. This is the nonlinear energy transfer that we've looked at before. And now this derivation takes and goes and defines a slow wave amplitude, which is simply the wave amplitude times e to the minus I omega kt. So this should be the slow amplitude, and everything is written in terms of the slow amplitude, which is a hat. Okay, so now we have a slow amplitude a hat, and then the derivation. So now you go through some zillions of algebra, very painful, admittedly, and you find an integral that looks like this. A fourth order term in terms of the slow amplitudes times this e to the I omega k minus omega p minus omega q. And now if you make the critical assumption that these wave numbers are slowly varying, you could take them out of the time integral, and then you get something like this. This is the slow wave amplitudes times this integral. This integral ends up being a delta function. This delta function is what forces us to have this relation that omega k is equal to omega p plus omega q. So this is the Hasselmann derivation of the resonant condition for a random field of internal waves. And it all relied on this assumption here that these slow amplitudes are slow enough that you can take them out of the time integral. So the critical assumption that is used to derive the condition on the W's, on the omegas, is that the slow amplitudes are slowly varying. So let's look at any questions about this. Okay, so let's look at these slow amplitudes. So this is for one particular wave number 44. So mostly horizontal wave. 40 is the horizontal, 4 is the vertical component, and the red as function of time is the wave amplitude, and the blue is the slow amplitude. So this is the critical point here. This is again the main explanation for that main result before. The blue does look like an envelope of the red, but it's not slowly varying. It has these wiggles on it that are rapidly changing, and that means that it's not slowly varying enough that you can take these slow amplitudes out of the integral, and we think that might be the reason that the derivation fails, and that's why maybe we don't get interaction mostly along resonance curves. Okay. So I'll stop here because, so again, if I had to summarize everything, the idea is this. We find interactions not just along resonance curves, and we think the reason is that the wave amplitudes are not necessarily slow. And this shows that they're not necessarily slow because the blue does look like a wave amplitude, but you see these wiggles on the blue that you'd want the wave amplitude to be sort of a slowly varying smooth curve, but it's just not in this particular simulation. And I think no one has actually looked at that. People just assume that it would be okay, but when you plot it, it seems not to work. And we think that might be the reason. So whether this applies to the real ocean, which is three-dimensional and there's Coriolis force, and we don't even have a Coriolis force and so on, so forth. There are many, many things that could have gone wrong here. But the theory of the resonant wave interaction and this kinetic equation should have held for this case that we're studying, and it seems not to do well. And the reason we think is the fact that the wave amplitude is not slowly varying. Questions? Okay, there's more, but I'm going to skip and jump directly to the conclusion. Thank you. Yes.
It does seem a bit slow. It seems like
Yes. Yes.
it's going along and then it jumps.
Yes.
It's like it's slow and intermittent.
Yeah, you see these wiggles here. Okay, so we quantified it in 2 ways. I was going to skip that, but let me show just one of them. So you can quantify the time scale of this by taking DDT of the slow amplitudes and divide it by the slow amplitude itself. And this gives you the time scale of variability of the slow amplitude. And then you compare that to the wave period and you find that it's not slow. And then we did a couple of other tests. So we tried to quantify this visual representation that I showed, and 3 different tests. So 2.5 show you that indeed the slow amplitude is not slowly varying as you would hope. Okay. I think you guys suffered enough today, so let me jump to the conclusions. So we have internal wave breaking is important because it's responsible for driving the large-scale ocean circulation. So it's an important problem to think about. We talked about resonant wave triads being those wave triads that satisfy both this and this. And this was meant to be a case where the energy transfer is especially efficient. So this is the basis for that kinetic equation for internal wave energy spectrum that has been very widely used in the literature since the 80s for internal waves in particular, maybe even from the late 70s. There's a wonderful paper by Bretherton and McComas that I think was very fundamental there. So we do these very idealized direct numerical simulations into the not super high resolution, double periodic, too idealized and everything and so on. And we try to see whether all this thing works for that particular non-realistic case. And we find that the interactions don't necessarily happen along these resonance curves. And the issue seems to be that the wave amplitudes are not slow relative to the wave period. And we admit that we need to re-examine this using more realistic situations, so 3D with Coriolis force and so on and so forth, not double periodic domain. So I would see this as a tentative result, but we're very excited about this regardless. Thank you. Questions about any of the two halves? Yes. We find something interesting that we're looking at now, that if you take horizontal stripes here, instead of going along the curve, if you take a curve that goes horizontally here and take only interactions within that horizontal band, then that explains very nicely the evolution of the energy. So we wonder, why is it that these horizontal stripes are actually, you see these horizontal stripes, why are these the place where the energy transfer is more efficient? We're trying to understand that. So again, I worry admittedly that these are horizontal stripes for this particular problem we worked on that has a specific geometry. Maybe they would not be horizontal for a more realistic problem. So, but the goal would be now to not just say that it doesn't work along the curves, but why is it that these are efficient is what we're trying to understand. Because it does look like you don't need all of the interactions, you just need these horizontal stripes here. You know, if you take just this spot here, only these wave numbers, you get a very good description of dE dt at the wave number k. We actually tested that. So we're trying to understand, why is it that these are important? Not only why the resonant curves are not important. Yeah?
So this is the end steady state energy. I'm wondering if during the transients you see energy amplified as the curve begins.
Interesting. No, we actually made a significant effort to reach that statistical steady state and analyze that only, and that was very painful. Why you think that would be interesting, the transient leading to that? You might be right. Yeah. But you know, there's an energy cascade at a statistical steady state. We're forcing only at very low wave numbers. So k equal 1, 2, in both horizontal and vertical direction. And the energy goes to other wave numbers only through these nonlinear interactions. And then the energy goes all the way to the scale where it's dissipated in the model. This is the Craig Winters flow solve model. So at steady state, you'd expect that energy cascade to happen along these resonant curves, and it doesn't. Maybe the transient is also interesting, but we haven't analyzed it. I think typically when that kinetic equation is derived, then it stops there. I'm not familiar with the further extension of it that leads to, you know, instead of just 3 ways, 5, 6, 7, there might be something, but I guess that's my ignorance here. Maybe Nico knows. No, okay, great, yes?
I have 2 questions, one on the first part, one on the second.
Okay.
On the first part, so what I used to teach the D courses, the wind blows with the Southern Ocean, could exceed these slopes and background visibility. Now you're saying the interior stratification sets the slope. That would mean, like, if you work it in reverse, it would mean that the interior stratification sets the rate of background visibility and the kinetic energy, and then the balance between the energy. Like, how does that propagate back to the balance?
Yeah. I mean, as you know, this idea that the slope is equal to tau divided by FKGM is correct only if the residual circulation is zero. Maybe when there's diffusion here and upwelling, the residual circulation is not zero, and that violates the condition that leads to that particular relationship, and that can change the slopes here. Say again, what's the?
Are you saying that it sets
No, I think I would guess that, this derivation that leads to S rho equal tau x divided by F kappa GM, that derivation relies on zero residual circulation. And my guess is that assumption of zero residual circulation depends on there being no diffusion in the interior, and that might break down and lead to changes to the slopes. And the other one?
So you define the amplitude as a multiplied by this oscillating exponential.
Yeah.
Yeah. That's a very punishing criteria for oscillation, especially when the viscosity diffusion of the embedding, any spectral peak will have some weight. So people would, I would assume it would apply maybe windowing.
I see what you're saying.
Yeah, I fall.
Yeah. I mean, you could be right that this way of defining the slow amplitude is not perfect. I think you're right. But I can say the following. In the linear case, this is the perfect, if in the linear case with no dissipation, no nothing, this leads to A hat being just a constant, right? Okay. Two, in the derivations, you look at the Hasselmann derivation, they actually use this as this is how they define the slow amplitude. So we're following their derivation. You might be right that it would make more sense to define some average time window average as opposed to that. But the derivations actually use this as the definition for the slow amplitude. That leads to this condition with the delta function. So I think this definition is critical for getting the delta function over the omegas in their derivation, even if it's not the optimal way of getting the slow amplitude. What?
What the simulations look like? You have data structures that pop out.
Yeah. That's right. You see, I was going to include that. Yeah. Anyway, you see, there's a stratification that we prescribe with n squared being the buoyancy period being 30 minutes. So you see isopycnals and they move in waves. And then if you look at the U and W, the horizontal and vertical velocity, you see patches moving around due to the internal wave. So you see basically random patches moving all around. I should have included the animation of that. But that's what you see. You see the isopycnals moving. There's no wave breaking in this simulation. We make sure that the forcing is weak enough that there's no wave breaking. But there's just waves that propagate their energy to smaller scale and then it dissipates due to the dissipation in the model. So that's what it looks like in terms of physical space. Yeah.
But the fact that if you're getting turbulence occurring intermittently, it just spectral theory really struggles with that.
I mean, the patches are just because it's a random field of internal waves moving around, many waves. So this leads to this randomly looking patches that propagate around randomly. I think that's an unavoidable consequence of having a random field of internal waves of all wave numbers following some spectrum.
Question online. You were assuming three-wave interactions in a certain way, could higher order approximations reconcile the discrepancy you see. And they followed that by the fact that the high density regions appear not on but near the triad curves amplifies this suggestion.
So the question is, can we get higher order interaction, not just 3 waves? I think, so that was asked before. I think there's probably a way to then go to the next order and include more than 3 waves, but for internal waves, 3 waves is the smallest number of waves for which you could get resonance interactions. For surface gravity waves, you have to go to 4 waves for the first one. I'm just not familiar with the perturbation analysis that then goes to the next order and have more waves. I'm sure that can be done. So who knows, maybe that would help. And yeah, so I think that would be my answer, basically. Great. All right. Thank you for persisting today.
Sorry, if I stressed you out. Promise I won't be in a different seat
No,
tomorrow.
no, don't worry. Just joking, basically, understand.
The 11th floor. It's.
I'll cover quick thoughts for you when you have a second. About that, are you
Sure.
busy?
No?
So the first one is this, I worked on this triad thing a lot in the gravity surface capillary wave.
Surface capillary.
Surface gravity capillaries are also triads.
Right, okay. yeah.
So same algebra, you know. So the first thing is that, that this delta functions and the kinetic equations in infinite time argument. And,
That's right.
and people normally get it, from like a complex plane, letting it down, go to 0. But you can actually solve for it, what that, what that looks like for finite time. And for
Is
finite-
a broader.
Yeah, for finite time, there's an exact solution, and it's I don't know if you know a Dirichlet kernel, it's like a sinc function, like a sin x over x.
Yeah, yeah. cool.
So what you get is you get the sinc function wrapped around
That's
the
right.
resonance curves, and so then the wave out.
Right.
So for any finite time, it won't be exactly there, it'll be kind of distorted.
But you saw that this wasn't the broadening.
I know, I did.
Yeah, yeah.
But
No,
then-
I'm aware of that.
Okay.
We actually use that in our favor because when you have just a 2-dimensional simulation, you may not resolve the exact curve. So you do need it to be a finite width.
Right.
To say that there actually, you need to make the case that there are actually resonant wave interaction. And so we have to rely on the fact that the curves are broadened, and they're broadened for 2 reasons. One is the one you mentioned, and the other one is the nonlinear itself leads to some broadening. So we rely on both of those.
Sure.
So,
Yeah.
so that to actually have resonant wave numbers.
Yeah, yeah. So the other question for you was, so in the gravity capillary case, so basically what you're showing when you show these resonance curves and where the MG is,